All right, buckle up, everybody, because today we are diving into a question that is sending shockwaves through the world of cosmology. Could dark energy, the supposed driving force behind the universe's expansion, actually be, well, an illusion?
It's a pretty bold question, and all the sources you send over, research articles, those scientific papers, even your personal notes, they all point to this seriously radical idea. They call it timescape cosmology.
Yeah, this isn't just some tiny little tweak to how we understand the universe, right?
Yeah.
This theory could completely flip what we thought we knew about its age, the structure, maybe even time itself. But before we get too far ahead of ourselves, let's do a super quick recap of the basics.
Right, so the current model, the one timescape cosmology is taking on, that's based on the Big Bang and Einstein's theory of general relativity. We picture the universe, starting from a single point and expanding outward, like when you blow up a balloon. And then you've got dark matter, this invisible stuff acting like scaffolding, holding galaxies together. And of course, the cosmic microwave background radiation. It's like the faint afterglow of the Big Bang.
So for a while, it seemed like this standard model was doing a pretty good job explaining things. Then, late 1990s, scientists discovered something that really threw a wrench in the works. The universe wasn't just expanding, it was accelerating.
Yeah, exactly.
It's like you're expecting a car to slowly coast to a stop, but then it suddenly slams on the gas.
You got it, and that's where dark energy comes onto the scene. Scientists proposed this, mysterious force, kind of like an anti-gravity, to explain this accelerating expansion.
So dark energy, this force that's supposedly pushing everything apart. But wait a minute, from the sources you sent me, it seems like some cracks are starting to show in this standard model.
Yeah, there are definitely some puzzles that have popped up. One of the big ones is this thing called the Hubble tension. Basically, different methods of measuring the universe's expansion rate, they're giving us different values for the Hubble constants.
So we're getting these conflicting answers about how fast the universe is expanding, which means maybe our understanding of dark energy, the thing driving that expansion, could be wrong.
Exactly. And just last year, the Dark Energy Spectroscopic Instrument, they call it DESI, released some findings, and they're hinting that dark energy might not be constant. It might actually be changing over time.
Oh, wow. So there's a lot of uncertainty surrounding dark energy. And that's where this timescape cosmology comes in.
Right.
The idea that maybe, just maybe, time itself isn't constant throughout the universe.
That's the core of it. Timescape cosmology suggests that time flows at different rates in different parts of the universe. It's all influenced by the distribution of matter and, of course, gravity. You remember Einstein's theory of general relativity? The one that says gravity can warp time?
Oh yeah, like how clocks run slower in stronger gravitational fields. So you're saying massive objects, like these huge galaxy clusters, their clocks would be ticking slower compared to those vast cosmic voids, those emptier areas of space.
Exactly. And here's where it gets really mind-blowing. Timescape cosmology says that time in those dense galaxy clusters, it could be running like a third slower than in those cosmic voids. We're not talking about tiny little differences here.
Okay, that's incredible. But I'm still trying to connect this to the whole accelerating expansion thing. Are we basically seeing some kind of time warp mirage?
I think that's a pretty good way to think about it. Timescape cosmology suggests we perceive acceleration because we're looking through these cosmic voids where time is running faster. The light we're seeing from those distant galaxies, it's traveled for billions of years, right? And because time's been moving faster in those voids, those galaxies seem farther away, and they seem like they're moving faster than they really are.
So instead of dark energy pushing everything apart, it's more like the relative speed of time. That's creating this illusion of things speeding up, this accelerating expansion.
Precisely. Think about it like this. You have two runners, one on a treadmill that's slow and one on a treadmill that's much faster. The one on the faster treadmill, they're going to look like they're pulling ahead, even if they're both running at the same speed, right, Kay? It's not that one runner is pushing the other, it's the difference in the treadmill speeds. That's what creates the illusion.
Okay, I get it. So these different speeds of time, they could be creating this effect where it looks like the universe is accelerating, but maybe it's not really.
Exactly. It's a pretty bold claim. It really challenges how we think about the universe working.
Now, I gotta ask, how does this timescape cosmology deal with the Big Bang? If time is flowing differently everywhere, wouldn't that mess with our understanding of how the universe started?
That's a really good question, and honestly, cosmologists are still figuring that part out. Remember that cosmic microwave background radiation, the afterglow? Well, that radiation has traveled through areas where time flows differently, so its properties might be, distorted. and we haven't fully figured out how to account for that yet.
So it's possible that this theory could give us a whole new way to interpret the Big Bang. Maybe it could reveal details we've missed, because we've been assuming time is the same everywhere.
Exactly, and that's what makes this so exciting. It's forcing us to re-examine some of our most basic assumptions about the universe, and to consider these, well, entirely new possibilities.
Okay, I'm hooked. But I'm sure there are a lot of skeptics out there who aren't ready to ditch the standard model and its dark energy explanation.
Oh, absolutely. Any new scientific theory is going to have people who are skeptical, and Timescape Cosmology is no different. Some people argue that it relies too much on one type of supernova, type Ia supernovae, to measure distances in space.
And a standard candle is, sorry, any quick refresher?
Oh, no problem. A standard candle is like an object in space. Its brightness is known. We compare how bright it actually is to how bright it appears to us, and that tells us how far away it is. Think of it like a light bulb. If you know the wattage, you can guess how far away it is based on how bright it looks.
Right, that makes sense. So these type Ia supernovae, they're like cosmic light bulbs helping us measure distances.
Yeah.
But some scientists are saying these supernovae might not be as standard as we thought.
Yeah, some critics say their brightness could be affected by other things besides just distance. And that could mess up our measurements, maybe even throw off the calculations that support timescape cosmology.
So if those supernova measurements are off, that weakens the case for this theory.
It's definitely a possibility. Another criticism is that timescape cosmology has some trouble explaining stuff that the standard model does well. For instance, the cosmic microwave background radiation, it shows these tiny temperature fluctuations. And those are thought to be the seeds for the large-scale structure we see today, galaxies, clusters, all that.
And how does timescape cosmology explain those fluctuations?
It's still a work in progress, They're actively working on models that can explain these variations, but with time flowing differently, it makes things more complicated.
So it's a puzzle they're still putting together.
Exactly, and that's what makes this whole thing so exciting. There's still so much we don't know, so many mysteries to solve.
Now, there was another criticism you mentioned earlier. Peculiar velocities of galaxies. What are those? And why are they a problem for timescape cosmology?
So peculiar velocities, they're basically how galaxies move, but not just with the expansion of the universe. They also move within their local environments because of gravity from other galaxies and clusters.
So it's like they're drifting on these cosmic currents.
Yeah, that's a great way to put it. Now, the standard model, it's got ways to explain these peculiar velocities. But for timescape cosmology, where time itself is different in different places, it's trickier to include these movements into the model.
Because if time is flowing differently, wouldn't that also affect how we measure those peculiar velocities?
Exactly. It's like trying to measure how fast a boat's moving when it's getting tossed around by waves. You got to factor in both the boat's movement and the water's movement, right? And with timescape cosmology, we're trying to measure galaxies moving through areas where time itself might be changing.
Whoa! Okay, that's a lot to take in. But even if this theory isn't the ultimate answer, it seems like it's making us think differently about the universe.
That's what's so valuable about it. Even if a theory is wrong, testing it and trying to make it work can lead to new discoveries and new insights. It's like climbing a mountain. Even if you don't make it to the top, you still get a whole new perspective on everything.
I love that analogy. It reminds me of something you said before. Science is always changing. It's not about sticking to what we think we know. It's about being open to new ideas and letting the evidence lead the way.
Exactly. And when it comes to cosmology, we're lucky to be living in a time of so much discovery. We've got new telescopes and instruments coming online all the time, and they're giving us data that will help us test all these theories in ways we never could before.
Yeah, you mentioned the Euclid Space Telescope before. How will that help us investigate this timescape cosmology idea?
Well, Euclid, it's designed to create a 3D map of the universe. It'll cover these huge cosmic distances and different periods of time. It'll be like watching a time-lapse video of the universe, showing us how galaxies and clusters have changed over billions of years.
So we'll actually be able to see how the structure of the universe has changed.
Yeah.
And that could give us clues about dark energy and whether timescape cosmology is on the right track.
Exactly. And there's more. There's the Nancy Grace Roman Space Telescope coming up. That one's going to be even more powerful than Hubble. We'll be able to see even further back in time.
Wow. It sounds like we're entering a whole new era for cosmology. With all this new data coming in, who knows what amazing discoveries are waiting for us.
It's a really exciting time to be asking these big questions about the universe, but it's important to remember that we need to be careful with the data, to be skeptical and think critically.
You're right, we can't just get caught up in the excitement and jump to conclusions. But we can let ourselves be amazed by what's possible and appreciate the work of all these scientists who are pushing the limits of what we know.
Speaking of what's possible, there's one part of Timescape Cosmology we haven't talked about yet, and it has some really mind-blowing implications.
Really? I'm all ears.
Well, if this theory is right, it means that how we see the universe's history, its beginning and its end, is totally shaped by where we are in it.
Wait, are you saying that the age of the universe, the entire timeline, could be different depending on where you are?
That's exactly what Timescape Cosmology suggests. And that leads to a question that people have been thinking about for centuries. If time flows differently in different places, does that mean how we see the end of the universe, its ultimate fate, is also relative?
Whoa, that's a big question. And I think it's the perfect place to stop now. But before we go, can you unpack that a little more? What does it even mean to say that how we see the end of the universe could be relative?
Well, that's a conversation for our next and final part. I'm really looking forward to diving into those philosophical implications with you and to exploring some of the questions Timescape Cosmology raises about our place in this vast universe.
I can't wait. This has already been one of our most mind-bending deep dives yet. So for everyone listening, stay tuned, because next time we're going even deeper into the mysteries of time, space, and the ultimate fate of the universe. We'll see you then.
So welcome back. I'm really excited to keep going with this Timescape Cosmology thing. But before we jump back into the specifics, I think it's worth mentioning there's a whole bunch of these alternative gravity theories out there, all trying to explain the universe, in ways that challenge Einstein's general relativity.
Oh, yeah, that's right. I remember seeing something about those in my notes. It's like this whole hidden world of cosmic explanations that most people have no idea about.
It really is fascinating, and it shows how science is constantly evolving. Like there's this thing called modified Newtonian dynamics, MOND. It suggests that gravity acts differently at really large distances, which might explain how galaxies rotate without needing dark matter.
So instead of needing dark matter to explain why galaxies spin the way they do, MOND changes the laws of gravity themselves.
You got it. It's a radical idea, but some physicists are starting to take it seriously. And then there's FR gravity, which tweaks Einstein's equations in a way that could explain the accelerating expansion without dark energy.
So it's like we have all these different teams of cosmic detectives working on the same case, but using different methods. Some are focused on dark matter, others on dark energy, and then you have Timescape Cosmology saying, hey, what if the problem isn't the stuff in the universe, but how time itself works?
That's a great way to think about it. And just like in a good detective story, we got to look at all the evidence and see which theory fits best, if any.
Speaking of evidence, I remember reading some criticisms of Timescape Cosmology. Some scientists were concerned about how it uses supernova data, right?
Yeah, that's one of the main things people are debating. Timescape Cosmology depends a lot on type Ia supernovae to measure those cosmic distances. But like we talked about before, some scientists think these supernovae might not be as standard as we assume.
So their brightness could be affected by other things besides distance, which could mess up our measurements and maybe even disprove Timescape Cosmology.
Exactly, and it's a valid concern. To really test this theory, we need to be sure we're using the most accurate measurements possible.
Okay, that makes sense. What about those temperature fluctuations in the cosmic microwave background radiation? You said earlier that Timescape Cosmology is still working on explaining those.
Right, the cosmic microwave background radiation, it's like a Beatty picture of the universe. And those tiny temperature differences, they're thought to be the starting points for the large-scale structures we see today. Galaxies, clusters, voids, all of that.
But if time was flowing differently back then, wouldn't that affect how those temperature fluctuations developed and spread?
Absolutely. And that's one of the hurdles for Timescape Cosmology. People who support the theory are working hard to create models that can explain those temperature variations, even with time flowing differently.
So it's like a puzzle they're still piecing together.
Exactly. And that's what makes it so exciting. There are still so many unanswered questions, so many mysteries to uncover.
Before the break, you mentioned another criticism. The peculiar velocities of galaxies.
Yeah.
What are those, and why do they cause problems for Timescape Cosmology?
Okay, so peculiar velocities, it's basically how galaxies move, but not just with the overall expansion of the universe. They also move within their local neighborhoods because of the pull of gravity from other galaxies and clusters.
So it's kind of like they're drifting along on cosmic currents?
Yeah, that's a great analogy. The standard model of cosmology has developed some pretty sophisticated ways to account for these peculiar velocities. But for timescape cosmology, where time itself is flowing differently in different places, incorporating these movements into the model is a lot more complicated.
Because if time is flowing differently, wouldn't that also change how we see and measure those peculiar velocities?
Exactly. It's like trying to measure how fast a boat's going when it's being tossed around by waves. You have to factor in both the boat's speed and the movement of the water, right? And with timescape cosmology, we're trying to measure galaxies moving through regions where the very flow of time itself might be changing.
Whoa, that's pretty mind-bending. But even if this theory isn't the ultimate answer, it's definitely pushing us to think about the universe in new ways.
That's what makes it so valuable. Even if a theory is wrong, just the process of testing and refining it can lead to new discoveries and insights. It's like, imagine trying to climb a mountain. Even if you don't reach the summit, you still get this incredible new perspective on the world below.
I love that analogy. It reminds me of what you said before. Science is always changing. It's not about being stuck in our ways. It's about being open to new ideas and letting the evidence guide us.
Exactly. And in cosmology, we're living in a time of unprecedented discovery. We have new telescopes and instruments being built all the time. They're giving us so much data, and it's going to help us test all these theories with incredible accuracy.
Yeah, you talked about the Euclid Space Telescope before. How will that help us figure out if timescape cosmology is right?
Euclid is designed to create this amazing 3D map of the universe. It's going to span vast distances and look back over billions of years. It'll be like having a cosmic time-lapse video showing us how galaxies and clusters have changed over time.
So we'll actually be able to see how the structure of the universe has evolved over time. And that could give us clues about dark energy and whether timescape cosmology is on the right track.
Exactly. And there's the Nancy Grace Roman Space Telescope, which will be even more powerful than Hubble. It'll allow us to see even further back in time.
Wow, it sounds like a golden age for cosmology. With all this new data coming in, who knows what amazing discoveries are waiting for us?
It's a truly exciting time to be exploring these fundamental questions about the universe. But as always, we need to approach the data with a healthy dose of skepticism and critical thinking.
You're right, we can't get carried away by the hype and jump to conclusions. But we can still be amazed by the possibilities and appreciate all the incredible scientists who are expanding our knowledge.
And speaking of possibilities, there's this one aspect of timescape cosmology that we haven't really touched on yet. It has some pretty mind-boggling implications.
Oh, do tell.
Well, if timescape cosmology is right, it means our understanding of the universe's history, its beginning and its end, is totally shaped by where we happen to be located within it.
Wait, are you saying the age of the universe, the entire timeline, could be different depending on where you are?
That's exactly what this theory suggests. It challenges the idea of a single universal clock and says the universe's timeline might be more like a tapestry with threads of different lengths. Each thread represents a different region of space experiencing time at its own pace.
So it's like one of those choose-your-own-adventure books where the story changes based on the choices you make. Except here, it's not about choices, it's about where you are in the universe.
That's a perfect analogy. It really highlights how diverse the universe could be. If time flows differently in different places, then the way stars, galaxies, even life itself evolve could be totally different depending on your location in this cosmic tapestry.
So instead of everything in the universe evolving the same way, each region could have its own unique cosmic dance, its own story unfolding based on its local time.
Exactly. It changes how we think about the universe, from one giant uniform thing to a collection of connected regions, each with its own history and maybe even its own destiny.
Okay, now I'm really starting to see how huge this idea is. But I gotta be honest, my brain is feeling a little overloaded trying to grasp all the implications. Let's go back to that question we left off with before. If timescape cosmology is right, could it mean that even our perception of the universe's end, its ultimate fate, depends on where we are?
It's a fascinating question, and it takes us to the very edge of what we know. Most of our ideas about how the universe will end assume that time is the same everywhere. They talk about the universe either expanding forever, becoming cold and dark, or collapsing back in on itself. The big crunch.
So those are the two main options, eternal expansion or a cosmic collapse.
Right, but what if those scenarios only apply to our little corner of the universe, to our own experience of time? What if, in other parts of the universe where time flows differently, things are ending in completely different ways?
Hold on, are you saying some parts of the universe might already be having their own big crunches while others are still just getting started?
It's a possibility, and it shows how Timescape Cosmology really challenges our usual ideas about cosmic beginnings and endings. If time isn't the same everywhere, then the universe might not have one single beginning or one single end. Instead, there might be countless beginnings and endings happening all across the universe.
I don't even know what to say. It's like the universe is this giant cosmic fireworks show with different parts lighting up and fading at their own pace.
That's a beautiful way to put it. It really captures that feeling of awe and wonder that Timescape Cosmology brings. It reminds us that the universe is so much more complex and mysterious than we often imagine. And there are still so many secrets out there waiting for us to discover them.
It's humbling, you know. We humans tend to think we have things figured out, but then a theory like this comes along and shakes everything up.
That's what I love about science. It's a constant process of asking questions, exploring, and changing how we understand the world. And in cosmology, we're dealing with some of the biggest questions humans have ever asked. Where did we come from? Where are we going? What is our place in all of this?
And Timescape Cosmology, even if it turns out to be wrong, is making us think about those questions in completely new ways.
Exactly. It's making us consider the possibility that our experience of time is just one of many. That the universe's story might be much richer and more diverse than we ever imagined.
It's mind-boggling, but also incredibly inspiring. It reminds us that there's always something new to discover, always something new to learn.
That's what makes exploring the universe so fascinating. It's a journey of discovery, a quest for knowledge that pushes us to the limits of our imagination.
Well, on that note of cosmic wonder and never-ending exploration, I think it's time to wrap up this amazing deep dive. But before we go, I want to thank our listener for sending us such thought-provoking material. You've taken us on a journey to the frontiers of cosmology, making us rethink time, space, and the very essence of the universe.
It's been a real pleasure joining you on this exploration. And to our listener out there, I encourage you to keep going on your own journey of discovery. Keep asking questions, keep exploring, and stay open to the endless possibilities of the universe.
And remember, even if we never completely unlock all the secrets of the cosmos, just the act of searching for them is what makes us human. It's what drives our progress and fuels our imagination. So until next time, keep looking up, keep asking those big questions, and never stop exploring the wonders of the universe. Welcome back, everyone, for the final part of our deep dive into this Timescape Cosmology. Before we took that break, we were really starting to think about this mind-blowing idea. What if our perception of the universe's end, how it all ends, is relative to where we are in it?
Yeah, it's a really profound idea to think about, We usually think of the universe's timeline like a straight line, beginning to end. But what if that's just how we see it because of how time itself works?
So instead of one universal clock ticking away for everyone, each part of space has its own unique time flow, its own way of experiencing time passing.
That's the core of Timescape Cosmology. It challenges the idea that cosmic time is the same everywhere, and suggests that the universe's timeline is more like, well, imagine a tapestry. It's woven with all these threads of different lengths, and each thread is like a different region of space, each one experiencing time at its own speed.
That's like those choose-your-own-adventure books, where the story changes depending on what choices you make. But here, it's not about choices. It's about where you are in the universe.
That's a great analogy, and it really highlights how incredibly diverse the universe could be. If time flows differently in different places, then the way stars and galaxies evolve, even life itself, could be totally different depending on where you are in this cosmic tapestry.
So it's instead of the whole universe evolving in the same way, each region could have its own unique cosmic dance, its own story unfolding based on its own time.
Yeah, exactly. It changes how we think about the universe, We go from seeing it as one big uniform thing to seeing it as this collection of connected regions, each with its own unique history, and maybe even its own unique destiny.
Okay, now I'm really starting to grasp how big of an idea this is. But I gotta admit, it's a lot for my brain to process, thinking about all the implications. Let's circle back to that question we left off with. If Timescape Cosmology is right, could it mean that our view of how the universe ends, its ultimate fate, is also relative to our location?
It's a really fascinating question, and it pushes us to the very edge of what we understand. You see, most of our ideas about the universe's fate assume that time is the same everywhere. They talk about the universe expanding forever, eventually going cold and dark, or collapsing back in on itself, what they call the big crunch.
So those are the two main options, eternal expansion or a cosmic collapse.
Right, but what if those scenarios are only true for our little part of the universe, our own experience of time? What if, in other regions where time flows differently, the universe is ending in completely different ways?
Wait a minute, are you saying that some parts of the universe could already be experiencing their own big crunches while others are still in their early stages?
It's definitely a possibility, and it shows how Timescape Cosmology challenges our usual ideas about cosmic beginnings and endings. You see, if time isn't uniform, then the universe might not have just one beginning or one end. It might have countless beginnings and endings happening all over the place, all at different times.
That's incredible. It's like the universe is this massive cosmic fireworks show with different areas lighting up and fading out at their own pace.
It really is a beautiful way to think about it. It captures that feeling of awe and wonder that comes with exploring these ideas. It reminds us that the universe is so much more complex and mysterious than we often imagine, and that there are still so many secrets out there waiting to be discovered.
It's really humbling, isn't it? We humans tend to think we have things figured out, but then a theory like this comes along and changes everything.
That's the beauty of science, you know? It's all about asking questions, exploring, and refining how we understand the world around us. And with cosmology, we're tackling some of the biggest questions humans have ever pondered. Where did it all come from? Where are we going? What does it all mean?
And Timescape Cosmology, whether it's the right answer or not, is definitely pushing us to rethink those questions in some really profound ways.
Absolutely. It's making us consider that our experience of time might be just one of many, that the universe's story might be much more diverse and incredible than we ever dreamed.
It's definitely mind-blowing, but also super inspiring. It reminds me that there's always more to learn, always more to discover.
Exactly. And that's what makes exploring the universe so captivating, you know? It's this constant journey of discovery, a quest for knowledge that takes us to the limits of our imagination.
Well, on that note of cosmic wonder and endless exploration, I think it's time for us to wrap up this incredible deep dive. But before we go, I want to give a huge thank you to our listener for sending us this thought-provoking material. You've taken us on an amazing journey through the world of cosmology, challenging us to rethink our understanding of time, space, and the very nature of the universe.
It's been a real pleasure joining you on this journey, you know, and to our listener out there, I encourage you to keep exploring, keep that curiosity alive, don't be afraid to ask those big questions, and keep your mind open to the incredible possibilities that the universe holds.
And remember, even if we never fully unlock all the mysteries of the cosmos, the very act of searching is what makes us human. It's what drives our progress and keeps our imaginations going. So until next time, keep looking up, keep those questions coming, and never stop exploring the amazing wonders of the universe.